All right, so let's keep going. We're still talking about forces. We are no longer just focusing on free body diagrams anymore. We are now focusing or using free body diagrams and how to find net force, everything that we've learned so far, and moving forward. All right, so what we're talking about today, excuse me. All right, what we're talking about today should not be anything new. You have talked about weight and mass forever and ever and ever, amen. All right, but what you should know by now, if you don't, is that weight and mass are not the same. All right, they are two very different things. All right, so that's what I want you to take away from this, is that weight and mass are not the same things. All right, so we have been using mass this entire year. We used mass a lot last year in chemistry. All right, so all mass is just how much stuff something or someone is made up of. So how many protons, neutrons, and electrons, how many atoms are comprising that object. All right, now one thing that you do need to know is that that amount does not change from place to place to place. All right, so our mass doesn't change from place to place. All right, the only way that you would change it is if you actually change the number of atoms that your body or an object was comprised of. All right, so say that you cut off an arm or something. I know that was kind of gory. I don't know where that came from. All right, but it's still the truth. All right, so if you like chopped off your pinky or something like that, you are no longer comprised of the same amount of atoms. So that would change your mass. All right, but say I was just trying to teleport you from here to the moon. All right, teleportation does not change your mass. All right, theoretically. All right, so you would have the same mass as you would have the same mass on the moon as you would here on Earth. It does not change. Now, what does change is gravity. Now, we know that gravity is everywhere, all right, but it's not going to be the same everywhere, right? So we know that gravity is that attractive force, all right? So it is, whenever we draw free body diagrams, gravity is always pointing down. That's because Earth is always pulling down. Earth's gravitational force is always pulling us down. All right, so I don't know where I was going with that. The force of gravity is everywhere, but it's always changing. All right, it's one of our four fundamental forces. All right, it's going to be the biggest one. We also have electromagnetic force. So if you split that up, that has to do with both electricity and magnetism. All right, last year in chemistry, we talked about the electromagnetic spectrum. All right, we talked about how it is created from electric waves and magnetic waves that are oscillating perpendicularly to each other. All right, another fundamental force is a strong nuclear force. So we have strong nuclear forces and weak nuclear forces, and those are just the forces that are happening between, say, like the nucleus, the protons and neutrons in a nucleus, and the electrons. All right, so gravity is the one that we obviously focus on the most. All right, so we know that gravity is pulling all things down, and we know that it causes everything to accelerate uniformly. All right, remember that if we throw a ball up, as it goes up, it slows down. As it comes down, it speeds up. So both slowing down and speeding up are both accelerations. And that rate of acceleration is always negative 9.81 meter per second squared on Earth. That's what we use on Earth. All right, so even if you have two different objects that have two different masses, all right, they will accelerate at the exact same rate. Now, even though we use that negative 9.81 and gravity is everywhere, even that negative 9.81 is not the same even on Earth. All right, if you go to this website, all right, you can go to the PowerPoint, click on it. It'll take you to a website called Wolfram Alpha. And you can type in any place on Earth and it'll tell you what the acceleration due to gravity is. And you'll see that there are places where it is 9.84, and then you'll have places where it's 9.73 or something like that. All right, so you'll see that even on Earth, that acceleration due to gravity changes depending on where you are away from the equator, how high you are above sea level, how below sea level you are. Anything like that can change the amount of gravity that's working on you at a time. All right, so that 9.81 is just an average for Earth. All right, so because gravity changes, our weight also changes. All right, our weight is just a measurement of how the gravitational force acting on an object depends or changes that object's weight. Pause. Let me re-say that. That didn't make sense. All right, so weight is just a measurement of the gravitational force that's acting on a mass. All right, an object is always going to have a mass. All right, so an object's weight depends on both the object's mass and the acceleration due to gravity. All right, so because acceleration due to gravity changes on Earth, then our weight would also change on Earth. Our mass would stay the same, but our weight would change. If we went to the moon has a lot less gravitational pull than Earth does, so our weight would change. It would go down on the moon as it does on Earth. All right, so what I really want you to look at is this equation right here. I want you to highlight that, circle it, bubble it, whatever you've got to do to know that this is super important. All right, so even though mass and weight are not the same, they are not synonymous, weight and the force of gravity are. All right, they are synonymous. So if I say weight, I'm also referring to force of gravity. If I say force of gravity, I am also referring to an object's weight. They are one in the same. Now, one thing that you have to think about is that whenever we draw a free body diagram, gravity is always pulling down. So all of our numerical values for gravity are negative. All right, but technically we can't have a negative weight. You can't weigh negative 10 pounds. All right, that's not a thing. All right, so weight is going to be the magnitude of the force of gravity. All right, but gravity is always pulling down. So if you are filling something out like this, your force of gravity will always be negative, but you can't ever have a negative rate. All right, weight, excuse me. All right, so the other day we derived our equation F equals ma. All right, so we derived that whenever we derived a Newton. So we took that a little bit further whenever we started talking about net force. So we know that if we have different forces working on an object, if we don't have balanced forces, then we have a net force working on that object. And that net force is going to cause some acceleration of some mass. All right, so we have seen both of these equations several times. But now we're still looking at this base equation, but we're going to be more specific with the force of gravity. So if we know force is equal to mass times acceleration, then our force of gravity is going to be equal times our mass times acceleration due to gravity. So our weight is equal to our mass times whatever acceleration due to gravity we have. All right, so if we want to figure out what we weigh on another planet, all right, we would take our pounds. All right, notice that weight is synonymous with force of gravity. So forces are all found in newtons. Well, if we step on a scale, our scales don't measure in newtons, they measure in pounds. All right, so the first way to figure out what we would weigh on another planet was to take whatever we weighed in pounds. All right, so let's just take 100 pounds. All right, so we turn pounds into newtons by using this conversion factor. All right, we know that 1 pound is equal to 4.45 newtons. So if we're 100 pounds, that's the equivalent of 445 newtons. All right, that's our weight on Earth in newtons. Okay, so that's the same thing as this 100 pounds. All right, so that doesn't really help us in any way whenever we're trying to find our weight on these other celestial bodies. All right, so we would then use this. All right, so this is our weight on Earth. So that's our FG on Earth. Well, we know that FG is equal to mg. Well, we just found our weight on Earth. We know that our acceleration due to gravity on Earth is 9.81. So we can use this equation to solve for our mass. And we know that our mass does not change from place to place to place. All right, so that would be 445 divided by 9.81. So 445 divided by 9.81 gives us a mass of 45.4 kilograms. All right, well, that's our mass. That is not changing. So if I wanted to find my weight on all of these other planets, I would just take my mass that I just got, 45.4, and then multiply it by each of these accelerations due to gravity. All right, so I would just take 45.4 and multiply it by 1.6 to find my weight on the moon. 45.4 divided by 3.59 to find my weight on Mercury. So on and so forth. All right, but what you would see is that you would weigh a lot more on the sun than you would on Pluto. All right, but your mass hasn't changed. Your body composition would not change. You could weigh I had somebody earlier today who weighed almost 9,000 pounds on the sun and weighed like 10 pounds on Pluto. All right, all that means is that they just have different amounts of gravity working on them. Their mass has stayed the exact same. All right, now whenever we talk about weightlessness, all right, weightless, you can never technically be weightless because we know weight is the same thing as the force of gravity. And we know that the force of gravity is equal to mass times acceleration due to gravity. All right, well, we always have mass and then we always have some amount of gravity working on us. So we're always going to have some weight. But weightlessness is just a sensation that you feel whenever you have all of your contact forces that are removed. All right, so whenever we step on a scale, all right, that scale is actually giving you the normal force that it is pushing up against gravity with. All right, so this is the free body diagram that we would draw if we were standing on a scale. All right, so the scale is giving us the normal force, which is great because it's still equal to our force of gravity, which is our weight. All right, but what if we put that scale in an elevator? I don't know why we would do it, but just say we did it. All right, so say we were standing on that scale in the elevator, and the elevator was going up or down at a constant speed. All right, what would that scale read? That scale would read our actual weight, all right, because the forces would be balanced. Well, what if we had an upward acceleration? Well, if we had an upward acceleration, that means that our upward force would be greater. That upward force is what that scale is reading. So I would weigh more on that scale. That scale would say I weighed more than what my actual weight was. All right, well, what if the elevator had a downward acceleration? That means that my downward force, that gravitational force, is larger than that upward force. So I would weigh less. That scale would say that I would weigh less. But what would happen if that tension force broke? All right, that cord broke. I would be free falling. All right, well, all that means is that my scale would not be reading anything. All right, so it would be like I was weighing nothing. All right, and that's what astronauts are experiencing. They experience apparent weightlessness because they don't have any normal forces working against that gravitational force. All right, so here we have our last thing. This one is what we are going to be working on for our practice today. All right, so we are given a book with a mass of 2 kilograms is resting on a flat table. All right, so before we do anything else, we want to draw our free body diagram for this. All right, so we draw our book. Well, we know gravity is pulling that book down, but it's not going down, 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 down. That table is keeping it up. All right, so we know that the table is a surface and all surfaces provide normal forces. Well, because that book is not going up and down, we know that those forces are balanced with each other. All right, so that's our free body diagram for that. So A is asking, what is the net horizontal force acting on this book? All right, well, there are no horizontal forces acting on it, so our net horizontal force is 0 newtons. B and C are asking, what is the force of gravity of the book and what is the normal force acting on this book? So we want the numerical values for these. All right, well, we know that Fg is equal to mg. We know that our mass is 2 kilograms, and we know that our acceleration due to gravity is negative 9.81. So 2 times negative 9.81 gives us negative 19.62 newtons. So if gravity, I'm going to rewrite this free body diagram right here. All right, well, if we know that gravity is negative 19.62 newtons, we know that for them to be balanced, normal has to be equal and opposite that. All right, so if gravity is a negative 19.62 newtons, that means normal is a positive 19.62 newtons. And D is asking for the net force. So we know to find the net force, we have to combine our forces. So what is positive 19.62 plus a negative 19.62? 0. So our net force acting on this book is 0 newtons. Now we could have answered that at the beginning because we know it's at rest. All right, and anything at rest has a net force of 0. So that's what we are going to be practicing. So not only are you drawing the free body diagrams, we are now able to put numerical values for both force of gravity and if it is balanced with anything else. So here it was balanced with a normal force. It could be balanced with air resistance, anything like that. All right, so if, as always, if you have any questions, just let me know.